So I think we might start. Thank you for coming. I just avoid any useless speech. We have so many interesting presentations. We have a wonderful program, I think. So just a couple of issues, because they've given you documents to sign in your package that is required for us, for our administration, to process all the payments and so on. So eventually you try to give them back as soon as possible to the secretary in the morning. Also, we ask you to sign an agreement to broadcast. We do not broadcast the Congress, but every way we tape it and eventually we make it available later, but we need the agreement of everybody. So our sessions, we have talks of we have 30 minutes for each speaker, about 25 minutes presentation and 5 minutes for discussion. And maybe we can start immediately with our first speaker, that is Norbert Henze. And the talk is Testing Multivariate Normality by Zeros of the Harmonic Oscillator in Characteristics Function Spaces. So.
Thank you very much. Today it's nice for working. So I have at the same time the challenge and the pleasure to give the first lecture. You see the title. The title doesn't reveal very much. So first I want to pose the problem. So the problem is very classical. We have independent copies, x1, x2, and so on, of a random vector x. These are all defined on a common probability space, independent, identically distributed. And suppose this calligraphic n sub d is the set of all non-degenerate d-variate normal distributions. So you see the expectation vector mu and the covariance matrix sigma. We want to test the hypothesis that the unknown distribution of x is some non-degenerate multivariate normal distribution on the basis of, let's say, the first n observations of x1, xn against general alternatives. So this is the general challenge. The standing assumptions in this talk is that the unknown distribution is absolutely continuous with respect to the Lebesgue measure. The first assumption. The second one is that n is at least d plus 1. So for any test statistic for this problem, there are some desirable features. The first feature is affine invariance, because the class of non-degenerate normal distributions is invariant with respect to full rank affine transformations. So the second property should be, I call it universal consistency. So hopefully such a test can really detect any alternative to a normal distribution. So this means the probability as n tends to infinity tends to 1, that the test rejects the hypothesis. The third property is applicability or feasibility. So of course you should have a good computer routine to evaluate the test statistic. It should work in any dimension, and it should work also for very large sample sizes. And the last property, you should know something also under alternatives. So of course there are fixed alternatives, there are so-called contiguous alternatives that converge to the null hypothesis at some rate. And of course if you know something under alternatives, you really see what kind of deviation measures such a test statistic if the hypothesis does not hold. So this test is based on a characterization of the normal distribution. Suppose this delta f of x is nothing but the Laplace operator in Euclidean D space. So this is a common notation. And suppose this is the Euclidean norm, and we consider a partial differential equation, which is a special case of Schrödinger equation. You see the delta f on x, norm x squared minus d times f, subject to the condition f of 0 is 1, or equivalently, so you see this minus delta plus norm x squared minus d applied to f of is 0. So this equation is called, so this operator is known as the harmonic oscillator. And the theorem is that the characteristic function of the standard normal distribution in d-dimensional space, so this here is the unit, is here, let's say, is the unit matrix in Euclidean d space. Let's see whether, yes, this ID is the unit matrix. Is the unique solution of this equation. So this, of course, you have to prove. It's not too difficult. I will not give proofs here, only ideas, and I will skip the techniques. So this is the basic characterization. Now, the test statistic. So you see this memo. This is the basic characterization theorem. We have to estimate the mu under normality. Now we think of being under normality. So this is the estimator of the unknown expectation vector. This is the estimator of the unknown of the covariance matrix. And you see this is transposed. This means all my vectors are column vectors. So column times row is a matrix. So this is the empirical covariance matrix. Now there is the standardization of the sample. So you see the Sn to the minus 1/2. So this is the symmetric positive definite square root of Sn to the minus 1, which exists with probability 1 because of my assumptions, because of the standing assumptions. So this is the empirical standardization of the data. Psi n of t now is the empirical characteristic function of those scaled residuals. Of course, under normality, these should look close to normality, to standard normality. So we would expect this to be close to psi of t, e to the minus 1/2 norm t squared. If we apply the Laplace operator to this psi n, it gives this expression. And the test statistic does the following for a positive a, which is a smoothing parameter, and for this weight function, which is nice. The statistic is TNA for short. It is n times. N is only because it's the right, let's say, factor. And you see now this is the squared deviation. And this is weighted. This is the test statistic. And if you insert delta psi n and delta psi, it is nothing but this. If you look at the test statistic, you see as a tends to infinity, this tends to 0. And if a tends to 0, this will explode, because if a is equal to 0, this integral does not exist. So this would be the constant 1. So it is, of course, interesting what happens if a tends to infinity and a tends to 0 for the test statistic. So I have to look. So I think I started at 910, no? More or less. Yeah. The test statistic can be evaluated. So this is straightforward computation of integrals. Now you see the feasibility. So there is no computational burden. Of course, computers are fast. And this also works in higher dimensions. You also see the test statistic is affine invariant because it only depends on the scalar products of theynj and ynk, and this does not even involve the square root. So you only need Sn to the minus 1. So it is affine invariant. So what happens if a tends to 0 and a tends to infinity? So element-wise on the underlying probability space, we have the following. First, if we let a tend to infinity, so this tends to 0, but if you blow it up with this exponent, it has a limit. And the limit is this. So this is a fairly well-known statistic. I will give information later, but this is really a pointwise limit on the underlying probability space. B So I told you if A tends to 0, it explodes. What happens if A tends to 0? You have to multiply it. You see A to the d half, which tends to 0. This has a limit, and the limit is nothing but this statistic. This is also one of the oldest test statistics for testing normality. So these limits, the first one is a skewness measure. This was introduced by Mori, Rohatky, and Sikkerly in the 80s. Oh no, it was in the 90s, beginning of the 90s. But the other measure is a measure of kurtosis introduced by Madhya in the 70s. A very old measure. So this, you see, this class of tests, if you consider A as a parameter, is in some sense closed at the boundaries. A tends to 0 and A tends to infinity, and gives something that is known. So this, of course, you have to do some calculations. Hopefully more than one person independently to see whether the results are correct. Now I give you a limit theorem which is able to show both the convergence of the test statistic under the null hypothesis and also under fixed alternatives to normality. So the assumptions here are the fourth moment exists. So this is really a basic assumption for these limit theorems. We can, without loss of generality, assume standardization, so unit covariance matrix and expectation 0 because of affine invariance. This is nice to have this. So this function m will play some role. This is nothing but minus the Laplace operator applied to the characteristic function of the standard normal distribution in Rd. I introduce a process Zn of t. Zn of t is something nice. If you see 1 over square root of n times a sum, you think of asymptotic normality, something. And what comes here is this. You do not see an imaginary unit, of course, which is in the characteristic function. You see here, this is the right centering if these were not the y's, but the original xj. It would be a centered process for the xj instead of the ynj. Here, what one has to show is the following, the proposition of, this is easy. You can really calculate very easily that this TNA is nothing but this integral, you see this weight function, the square of this process. And this gives you a hint. The setting here, the natural setting is that of a Hilbert space. You see those equivalence classes of functions which are almost everywhere equal because with respect to this measure which is generated by this weight function. This is the scalar product in this Hilbert space. This is the norm in this Hilbert space. And then you see the statistic is nothing but norm squared in this Hilbert space. So it is nice to have a central limit theorem. Then you can, of course, see what the asymptotic distribution is. So this is the main message here. So this is the memo. This is the definition of the Zn. And I told you I also want to tell you something under alternatives. For this, I introduce a mu. This is similar to the m. It's the mu. This is, let's say, if you think outside of the world of normality, so this is now a general alternative, which we have. And this is here the right centering, If here now we have the x's, and here the x's, and here the x's, you must replace m by mu. So we have this process. I call it Vn of t. This here is the right centering, the mu. If here we would have the x's, here xj, 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 then this is the right, it would be a centered process. And you see the Vn process is equal to Zn if we have a standard normal distribution, because then the mu is equal to the m function. So now I have to introduce the characteristic function. So this is under this alternative. I also have this psi plus minus, so this is the real part plus minus the imaginary part. I need the Hessian matrix of a function, call it H. I need the gradient, nabla. So these are standard notations. And now there is something which looks like a miracle, but this comes out after some calculations, hopefully done independently by at least one people. So on the first slide, there were two other people. I forgot to tell you, Philipp Dörr, who is a master student, and Bruno Ebner, who is over there. So we did some computations independently, all three. Now this function, you see v, tx, this is nice because it corresponds to this part here, norm squared, cosine plus sine. But then there are some other parts. Of course, this depends on the underlying distribution of the alternative. And what one can show and has to show is the following. So this is the Vn as a memo. The proposition is, if you have this process Vn tilde, and Vn tilde, you see, is a nice process because this is a sum of independent, identically distributed random elements in this Hilbert space, viewed as a function of t. Then you can show that these Vn tilde is near Vn in the sense that the difference measured in the norm of the Hilbert space tends to zero in probability. Of course, what you have to do is the following. These y and j, which are here, now you see this is the definition, xj plus, let's say, a difference. So the difference is nothing but this difference. And so you have to work with this difference here, here, and here. And to see what happens and what is negligible asymptotically and what is not negligible asymptotically. And for this, you need also the fourth moment here. So the theorem is this process, Vn, converges in distribution to a process V, and V is a centered Gaussian element of this Hilbert space. And the covariance kernel is nothing, I call it L, is nothing but this expectation. So you need this function V. So calculating this, you saw the V function was complicated, is even more complicated. But we calculated it under the null hypothesis. So this is a general result, which also holds under a general distribution. So the limit null distribution then is as follows, theorem. Suppose we have a non-degenerate normal distribution, and I need to introduce two abbreviations, D2 and D4, and we have the following. Under this null hypothesis, we have a random element Z of this Hilbert space. I here call the covariance kernel K, but K is only a special case of our L, and the covariance kernel looks this way. So this is under the null hypothesis. So you see no parameters at all. It's only a function of S and T, a complicated function, but you can calculate it. And we have V convergence. Zn converges to Z. And B, of course, now the continuous mapping theorem gives the limit distribution is nothing but, so if this is in principle well known, this is nothing but the norm squared of this process. And the distribution itself, from general theory, is an infinite sum of weighted chi-square, independent chi-square variates. What we did is we calculated the expectation. So by Fubini's theorem, the expectation is the integral of the expectation of this, which is nothing but the diagonal of the kernel. And also independently, we obtain this theorem. So you see, if you introduce some quantities, then this is the expectation. So this is the limit distribution, I call it this way. Here you can see how it behaves if D grows. So this is nothing but, so here is 1D, and here you see the third power. So it grows like a polynomial, but on the other hand, the D is also here in the pi and also here. So there are several quantities, but you see how it behaves. So the expectation. So what happens under fixed alternatives? I do not give you the result under contiguous alternatives, but I tell you the test is able to detect contiguous alternatives that approach the null hypothesis at the rate n to the minus 1/2, irrespective of the dimension d. So the dimension d does not enter. So fixed alternatives. So assumptions, As before, the fourth moment exists of the norm, centered without loss of generality. So this is the memo, so this is the function mu. This is the function m. M is equal to mu under normality. So the theorem is, first, some sort of strong law. So if we divide the test statistic by n, then it converges almost surely to something which is a measure of deviation from normality. It depends on the weight function and on the parameter, the tuning parameter of the weight function, which is nothing but this integral. So you see here the characteristic function under the hypothesis. This is standard normality. So you see the Laplace operator, and this is the measure of deviation. And this is nothing, if you do some calculations, this is nothing but, you see, the norm squared in this Hilbert space of this difference. And we have that this delta A is 0 if and only if we have normality. Together with this result on the null hypothesis, we have consistency against each alternative for which this moment exists. We conjecture that the test is all the more consistent if this condition does not hold, but it is much more difficult to prove. So we conjecture really that it is consistent against any alternative from normality. Theorem. We can also prove something on this measure delta A. So delta A itself also converges to 0 as A tends to infinity, but if you multiply it with this quantity, we have this, and you see you need the sixth moment here. And this is nothing but multivariate population skewness in the sense of Mori, Rohatky, and Szekely. The other way around, there is no limit theorem. A tends to 0. At least we didn't find one. What about asymptotic normality under alternatives? So notice this delta A is nothing but norm squared of z, and z is nothing but the difference of mu and m. So rescale the process Zn star, and then we will see very easily that this has an asymptotic normal distribution. Of course, this converges almost surely to delta A, so the difference tends to 0, almost surely. So multiply it with square root of n. So why there is asymptotic normality? So this is square root of n times, and now Tn divided by A is nothing but this, norm squared, and this delta A is also norm squared in this Hilbert space. And in Germany, we call it the third binomial formula. This is nothing but this, scalar product, if you calculate it. And the next step is, now, take this here, and now write 2z. 2z, there is an error, there's only plus 1, so plus Zn star minus z. Now take the first part with the 2z, and this first part, so this is nothing but 2 times, and now you see something nice. And the rest is, so give a square root of n here also to the Zn star minus z, and then you have to divide by square root of n. So plus, what remains is this, 1 over square root of n times something. And this is nothing but Vn. So this comes out, this is Vn, and this is also Vn, and Vn converges in distribution. So this means this here, because it converges in distribution, this is tight, divided by square root of n, it tends to 0. So the main part is this first part, and if this converges to a centered Gaussian process, by the continuous mapping theorem, the limit distribution is the distribution of 2 times scalar product of V, which is a limit process, with X, and this has a normal distribution in Hilbert spaces, a centered normal distribution. So the result is, theorem, we have asymptotic normality, and the variance may be calculated this way. So you need this covariance function L and this function Z. So the proof is very easy because the sigma squared here is, because of the factor 2, is 4 times, and now this is the limit distribution, the scalar product of V with Z. And if you write it this way, by Fubini's theorem, it is nothing but this, and this is the function L. And now the next nice thing, but you have to work very hard, is that this sigma squared can be estimated consistently from the data. And this gives you a possibility of having a confidence interval asymptotic for this measure of deviation delta A. So this is Samemo, so sigma squared is this integral. So you see L and you see Z. And L is an expectation. And V is a complicated function. And the Z is also a function. There is an expectation. And what you have to do, you have to replace each expectation by 1 over n times a sum. And each x by y and j, so by the scaled residuals. And also here in the characteristic function which enters here, so real, there are also expectations involved. So you have to place everything and see whether it converges. But you will get an estimator. It will take several slides to write it down. But it works. So now you have then something empirically, Ln and Zn, and this is the estimator. And you do not need to compute integrals. Each integral can be computed explicitly. So you see, we have asymptotic normality. By Slutsky, I can divide here by sigma n hat, and then we have a standard normal distribution as the limit distribution. So we have an asymptotic confidence interval for this delta A, which is here, given here. An example, very simple example, 1 dimension, 1A, level of significance 95%, 3 distributions, the uniform, the Laplace, the double exponential, and the logistic distribution. You can calculate those deviations, so you can calculate the delta A's. And you see now this is the empirical coverage by means of 5,000 replications. And if n is at least 50, there are the values are near 95%, so it really works. A last slide is a comparison of the new test with, let's say now, what is a standard class of test, the BHEP test for multivariate normality. So these tests work, let's say, essentially with the same measure of deviation, but without the Laplace operator. You see, this is missing, but otherwise it is the same. And this class exists for a long time. And this new class shows in many cases a stronger behavior. And for example, here you see the parameter A is from small to large to 10, 0.1 to 10. Here the same. And there are some alternatives. For example, a mixture of normals. I don't want to explain the parameters. You see what happens. The test here, n is 20, breaks down for larger values of A, but this is stable. So this is empirical power. The same, n is equal to 50, so this test has been proved to be consistent against each alternatives. You see, the power grows, 20, 50, here, also here. It will tend to infinity. This has been proved. But you see, it breaks down. And there are other alternatives, like a multivariate T distribution. So the same behavior. Or, let's see, this is a product of Laplace distributions. Or, let's say, this is some symmetric Pearson distribution with heavy tails. So there are interesting phenomena that might be explored also theoretically, and I think this is enough for today. Thank you very much. So.
Maybe I ask one, because you have A going to 0 and A going to infinity, one kurtosis and one. Could this be considered as a kind of linear combination or a weighted smooth test, Riemann smooth test?
No, there is really no linear combination. So the problem is really those boundary tests are not consistent against general alternatives. So they really have their deficiencies. And for any fixed A, there is consistency. We proved it against really any alternative, so that the fourth moment exists. So and there is really no linear combination in some sense. So this, I fear I cannot answer. So it is difficult to interpret such a delta A. Of course, this interpretation might help, because then for large A, it is near some skewness. For small A, it is near some kurtosis.
So I guess it was ruled out anyway by the assumption that it's possible if you have like a bivariate marginal normals, but it's not joint.
Pardon?
Suppose you have a multivariate vector with
Yes.
all the marginals are normal, but
Yes.
it's not joint.
Yes.
Something that you could also.
Yes, of course. It fulfills the condition. And I conjecture that really it is consistent against any alternative. But then, of course, so you must define the test statistic if you observe that your covariance matrix is not invertible. You must change or modify the test statistic. Yes, in the
I wonder, I don't know, instead of the second Hermite polynomial, this characterization is true for any Hermite polynomial?
I don't know. So we really proved this theorem. There might be a generalization, but I don't know. I cannot answer this question. This, okay.
So our next speaker, Marie Huskova.
Yeah, that's right. Okay. So at first, I would like very much to thanks for the kind invitation to participate in this nice workshop, and thanking to all coming for this to participate. So I will be struggling with having two equipments in my hand. Yeah. So if I keep like this, is enough? No. Wow. That's okay. I will try. So the title is. So is it okay? So the title is Monitoring Procedures in Two Sample Multivariate Situations. So this is kind of change point problem. There will be some expressions similar that were in the previous talk, but only very slightly. So here is somehow the structure. I will see how I will get. So the introduction, some online procedures, of course, asymptotics, some computational things, shortly resampling and applications and simulations. That's these things. The issue is at first what is meant by the title. So two sample multivariate change point detection. So the procedures are based on empirical characteristic function, L2 types, and the focus is on line procedures. So that means sequential things, where there will be asymptotic properties, simulations, and the short applications. So the motivation, what we mean is the following, that we are monitoring sequence of pairs of multivariate observation to see whether the underlying model that might have started being a stochastically equivalent remains true also in the future. So this is somehow see that it can be artificial, but we can find this type of problems in, say, in finance, and we have the performance of some indicators of two similar companies that are usually behave similarly unless something happens. Similar, if we have industry, we have two measurements within the production procedure, hydrometeorology, if we have these stations that are measuring the climate or temperature, etc., they should be similar. And then, of course, in medical research, there we have two patients that are at the beginning of treatment. They are almost the same situations, and they get different treatment, but the question is what will be. So this is roughly, so originally how we came to this was from the really medical research, when they were following a group of boys and girls, and concerning their sport results, said it appeared that there were small children, said up to a certain age, the children were, boys and girls were almost the same, but at a certain moment it started to be different. So that was the beginning of the whole business here. So then we found out that there are some other possible applications. Okay. So the formulation of the problem, that we assume that we have a time series, this is xt and yt, so this is a couple. We have assume that we have a stationary time series, and both are p-dimensional. And now what can happen is that we have that the sequence, that the series xt and yt are independent. That means that we have a kind of two-sample setup, or they can be dependent, and so that means this is a kind of pair setup. Both would be covered here. Certainly we have this online and offline, so that more will be on the online monitoring, so that means that one observation is coming after another, and we should decide always whether we should continue or whether some change is indicated. So this is just small thing. This is concerning Brexit elections. Data are from 2016, and said there is, you see this, the red line are the result of measuring, and there is this line that is saying that there is the Brexit, so the elections for it. So this is just, so that if we just look at it, so there is a change, but we should have the pair, so that will be later on. Okay. So here is more formally formulated. So for both situations, it's either two-sample or paired. So we assume that the null hypothesis that the distribution function are the same. So that means that the marginal distribution of xt and yt are ft and gt, and they are the same. They are equal to some k0, and this is fixed but unknown. And now we can consider two type of alternatives. One is that there will be a different effect, so that after a certain moment we have both distribution functions are the same. This is the k0, and this is at time t0 is changing to ft to kf and gt to kg, so that they are different. Okay. The other alternative that can be considered that they have the same effects, that we have the same distribution up to t0, then there is change in the distribution, but both distributions are changing and they are the same. Yes, so this is a different. Okay, so that can also happen. This is more difficult to distinguish the second situation. Okay. Okay, so again, the procedure will be based on the characteristic functions that formulated this h0 in terms of characteristic functions. We have that the characteristic functions are the same for all t, and they are equal some phi0, and this is unknown, etc. The procedure is based on these two type things that. Okay, sorry. Okay, so that we have this integral. We have a distance, or this should be the square of distance of these two characteristic functions, and we take integral of it with respect to some weight function w. Okay, so this is similar what we had in before. Clearly, as soon as the characteristic functions are the same and the weight function is properly chosen, it's positive, and if they are not the same, so that should be so I don't know, we have 0, otherwise it should be positive. Okay, so this is just measure behind it. And so concerning now online procedures, that the statistic for this situation is the following: as soon as we have t observations, so the test statistic that we use is this dt, this 1, and so this is a difference of empirical characteristic functions. This is just of x and y, so this is natural thing. And okay, so then one can easily see that if we have the situation this h1, so that means that there is an effect, so the distribution of these two groups are different after the change, so that's okay. But as soon as we have the other situation, when there is a change, if there is a change in both x and t, but again we have, after the change, they have the same distribution or the same characteristic function, so what we can expect that there will be, after the change, there will be probably something going slightly on, but afterwards it will not go. So it appears also in the simulations that it's not really properly working. Okay, so having the online setup that can be formulated in a number of ways, but it means that we are proceeding, the observations are coming one after another, and after each new observations we are making decision either to continue or to stop. So in this situation, the test procedure this is the test statistic we had on the previous slides. So this is based on this kind of function of these empirical characteristic functions. But here we need kind of standardization. This is one thing. In order we have a limit distribution under the null hypothesis. This is not singular. The other thing is that we have here this eta, which is kind of tuning constant. Okay, and it's just so that was used in other problems several times in before. If we expect early change, then this eta should be chosen slightly larger than 1, and otherwise usually we are choosing eta equal to, because it means some simplification. And what we said, there is a critical value. This is CT1 alpha. And what we said, it should be chosen in the way that as soon as t is tending to infinity, so we have the asymptotic level is alpha. So here is t is tending to infinity. And here is the consistency set. As soon as the null hypothesis doesn't hold true, so then it converges to 1. Okay. So here this is the issue that what is the issue that we assume that we can do. We can do maximally capital T observations, and it's divided by here. Okay. So this is what one can do. We will, how to get the approximation for the critical value that will follow from the asymptotics and some bootstrapping afterwards. Okay. So here is just another. So here are the elementary properties. So if we have the null hypothesis, the expectation of the difference characteristic function is 0. As soon as there is a change, so here is the expression for expectation. So it gives the elementary picture what we can expect. So what I've just mentioned here, that for this situation we have a t is finite. So that means that we know that we can do maximally capital T observations, but then this is usually called close-ended procedure. As soon as T is infinity, so we call it, it's closed, open, that now ended, but open. But then the modification would be needed. But we have also other possibility how to proceed, but it's only, this is in fact the motivation for this is coming from the procedure suggested by Chu and other, and Horvath and other. There is a series of papers, and it's based on the idea that we have a historical data of size m. They follow the null hypothesis, and after that we start monitoring, and then the procedure is like that we have the difference of the characteristic empirical characteristic function for x and y, and here we compare the empirical characteristic functions based on the training data, and here is based on the new data set. The idea behind it is clear, and there is just the standardization, but I am not going to talk more about it because it follows the idea used in before. Okay, so just we can consider also offline situations. That means that we have capital T observations, and we should test. We should test that. Then we can either use the statistic that we had here, even using the critical values, but yeah, it's somehow it's assumed that we have all capital T observations that can be used, but the other possibility is to provide the usual change point, this procedure that we are comparing empirical characteristic function of the pair of these observations based on the first T observations and T minus, capital T minus small t observations. So this is behind it. So this also we need some standardization. Okay. So there is that one can get the approximation for the critical value, but here is an asymptotic. So what is assumed that we have the alpha mixing sequence. I think that what is here needn't be true, that can be vacant, but we have it there. So then the weight function is assumed that it's non-negative, measurable, yeah, and it's symmetric in this way, and it has this property. And then we can show that this statistic that was for the monitoring has the same limit distribution as supremum over S. Here is S to power 2 eta minus 2, and this is the integral of square of Gaussian process, but this depends both on S and also on U. And there is a structure, how it looks like. So of course, this is not usable. Yeah, one can simulate it, but it's not good thing. So this is all this. Okay. So how we can use it also is the fact that for getting this sequential things to have the approximation for the critical value, we would need to have all observations set. Here we can use the following issue, just the approximation based on the first MT observations in the way that we can use from the theorem above that the test statistic, if we take max from 1 up to capital T, has the same limit distribution as if we take max only from M capital T up to capital T. And this is for MT tending to infinity, and the ratio is tending to 0. So that can be used in this way. Okay. Yeah, so this is sorry, the assumptions are here wrong, but nevertheless it shows the theorem is true, and it shows that this is in fact the consistent test. Okay. Computational aspects that to calculate this integral wouldn't be too pleasant. That one can just play a little bit with sinus and cosinus, and this statistic dt in W can be expressed as a sum of this type of sum, and here is an integral. And so this is, if we choose this weight function properly, so that is in fact its characteristic function of this x. When it is symmetric, so it's written there. So what is typically chosen for this situation, that we take that this is e2 minus, and here is a norm, usually Euclidean norm to power gamma, where gamma is between 0 and 2. Okay, then we did cover both Cauchy and normal distribution, and there are also some other possibilities. So this can be relatively easily calculated, so integral is not needed. Okay, so the resampling. So if we have independent observations, of course, it's easy that we use classical saying that we have the, I would say, kind of, almost naive bootstrap. So this is the procedure that was a long time ago proposed by Claudia Kirsch, which is somehow done that we are just taking the first M observations and use the classical bootstrapping for IID situations and get new observations, just taking always from the historical samples. So this is described here. As soon as we have dependent situations, this is somehow there is used the block bootstrapping, but somehow it's not working so nice as it was expected. So how much time do I have? 5 minutes. Okay, just shortly. So there were a lot of simulations done. So I would probably show only time series. I said it's okay. Sad here is say if we have the R autoregression of order 1 sad, we have, you see here is sad, what is here? It means dependence. Here is H0, T is 50, 100, 200, and we have, you see this is H0 means, H0 means, this is under the node, so that means what are the empirical level. Set for 50 it's so. This is the power when the change is in the mean, and this is when it changes in the sigma. And so that it's clearly what we expect, that as soon as T is increasing, so that we get better power. But you see there was several questions connected with it. Side. What is here? It's probably not so easy to read, but the questions that we got was, okay, you are sure, you are said it's theoretically is working for any P, but what is happening as soon as P is becoming larger? Said it's here what is happening. If we have P2, 4, and here 10, said it's true that here the level is reasonable, but as soon as P is becoming larger, said it becomes more and more conservative, but the test is becoming, the power is okay. Okay, so the issue was, but it's unfortunately it can't. So the issue is the following: we had there also constant A in that weight function W, and so the question is how we should choose as soon as P is increasing, and it appears that we should choose this A should be depending on P, and it's not possible to read, but somehow it should be typically be, it should be square of the dimension there, so that it's somehow working, but no theoretical results. And the issue is, another issue was the change in skewness and kurtosis, that it's of course, it's based on the characteristic function it is. And again, the question was what is happening if the dimension P is becoming larger, but I think that it's not, yeah. Okay, and I think that I have probably 1 minute to show the data. So these are the data concerning Brexit. We have, it's sad what is above, it's, these are the stock indices, this is BATS and this is NISA, okay? And the lower, this is the red graph, it's corresponding, the exchange rate, pounds, British pound with respect to euro, and the other thing is US dollars with respect to euro, okay? So that what can be seen just naively here, that here is the time of Brexit. I mean the Brexit, when the election was, there is where we see the difference. So then just, okay, so then you can use several tests. Mostly it was rejected, so that means that the change has appeared. And here is, okay, this is corresponding to situation up to here. So this is what is in the bold. So that was up to the training sample or historical data, and then afterwards the procedure proceed. And here is one of the statistics that we have. We have after beginning of May that was used as a training sample, and then we see that it's starting to grow, and it goes above the critical values later on, sometimes in August. That's why. Okay. But it doesn't say when the change occurred in this ratio. So I think that it's everything. Thank you very much for your attention. Are there any questions?
Ma'am, nice talk. I just have a quick question. So, as you are considering like a norm difference between characteristic functions, it seems intuitively very analogous to energy distance, and there are some like non-parametric change point detection methodologies based on energy distance, but maybe for independent data. I was just curious to see how does your method compares to them, if you have any thoughts. Thank you.
This part is in fact in the paper, which is, this is in the paper. There is a relationship. If you just play with it, I think that Simos Maintanis could say much more about it. So that if you have the test statistic and you are playing with this constant A, you get this energy statistic. So in fact, this is more general. Okay?
Thank you.
Other questions? So let's thank again our speaker. Is Maria Jimenez Camero.
I think I don't need this device. Maybe I can. No. Let me try. Yes. Okay. First, thank you for the organization of this nice workshop, or also for inviting me. So the title of the talk is on the GOFCP test for functional data. I am going to repeat some ideas from the talk of Norbert, who is a co-author. Yes? Because they have to record. Okay. So, first I'm going to review some key ideas from the finite dimensional case, and then we will move to the infinite dimensional case. So, in finite dimension, the normality assumption is a crucial, because there are, even nowadays, many procedures that assume normality. This motivates that there is a huge number of normality tests. Some tests are based on properties that characterize the normal distribution. An example is, for example, the test that explained Norbert at the beginning. But there are many other tests that are based on comparing a non-parametric estimator of a function that characterizes a law and a parametric estimator. In this second set, we find the test by. I'm going to show. Is this working? This is not working. I don't. Well, yeah. The red. It should. Maybe I am doing. Okay. A member of this class is the VHEP, that is called this way because it was initially proposed by Epps and Poulet for dimension 1, and later it was extended for any dimension by Baringaus and Hens. Because of the nice properties, it was initially proposed for II data. But because of its nice properties, it was extended to other contexts. For example, for testing normality for the errors in linear models, for the errors in non-parametric regression models, for GARCH model, and so on. This is infinite dimension. For example, but the normality assumption is also an important assumption in other settings. For example, in our case, in functional data analysis. Why? Because in general, most procedures are non-parametric, but in some cases, some procedures assume normality. I have now. For example, there is in this book they propose a test for the quality of covariance operators that assume normality. Some tests assume also some other tests also assume normality, and there are other methods that, although are designed for general case, when the normality assumption is true, simplify a lot. So the testing for normality is also of interest in this setting. The point is that there are few tests for testing goodness of fit in this setting. To my knowledge, to our knowledge, there are the tests of Cuesta Albertos and colleagues, but that are based on random projections. This paper, Buchni and others, propose a Kramer-Bonnice type test comparing the distributional functional, but it assumes that under the null we know everything except for a finite dimensional parameter. And the test in this paper that is designed for a simple null hypothesis. Okay, but so I forgot to say before because Norbert said before, but anyway, I'm going to repeat. The test by the VHP is based on comparing a non-parametric estimator of the characteristic function to a parametric estimator. Because every probability distribution of a random element taking values in a separable Hilbert space is uniquely determined by means of its characteristic function, our proposal is to try to extend this test to the functional data context. Well, a small review. I need this review, sorry. Some parts are repeated. So, the VHP for IA data takes these Y's that, as said Norbert, this, at least for large N, should resemble a random sample for a standard normal distribution. So the VHP compares the empirical characteristic function of these Y's to the characteristic function on the standard normal distribution. The test is a L2 norm defined this way. This is a weight function, but forget it. Some properties. It's consistent, is able to detect continuous alternatives. It has a closed expression, and from this closed expression, we see that the test is invariant with respect to full Planck affine transformation. This is really important. Why? Because the family of normal law is invariant under full affine transformation. So it would be a good property. Okay. This is the original version of the VHP test, but we can propose more versions. This is the following. Recall that originally the test was proposed for dimension 1. And taking into account that X is divariate normal if and only if every projection is univariate normal, we could look at all projections, calculate the univariate statistic, and, for example, take the maximum or integrate. Okay. We will have a look at this. No, we are not going to have a look. We can integrate. We can integrate for here what we can do is consider a measure on all possible vectors. And as for adequate choice of this measure, we have a statistic with the same properties. Believe me. Believe me. Believe me. Now, the interesting part. Yes, because what we are going to do is to imitate the old one and the new one. So some usual this terminology is taken from the book of Horvath, which is here. So let us consider the space of function with square integrable in 0, 1, with the usual scalar product, the usual norm. We will assume that this moment condition is satisfied, which ensure that the mean exists and also has a covariance kernel with associated covariance operator defined this way. The mean and the covariance operator can be consistently estimated by these estimators, which are the usual. This is just to state some notation. Okay. The characteristic functional of a random element taking values in a Hilbert space is defined this way. It's the same in the finite dimensional cases with the scalar product. By definition, a random element is Gaussian if and only if the characteristic functional takes this form. So, testing Gaussianity. In finite dimension, we talk about normality, and in infinite dimension, we talk about Gaussianity, but I will check. So, the null hypothesis is there. And I would like to do some observation. Here, the null hypothesis is that the characteristic function has this expression, and here we have two parameters. But the parameters are mu, which is an element of the Hilbert space, and one operator, which is symmetric definite. So the parameters has infinite dimension. So the above test cannot be applied. Can apply. So when we try to extend, we found two main problems. The first problem is the dimension. We cannot fight against dimension. Because the main problem is that for any sample size, the span of the data is strictly contained in the space. While in finite dimension, at Norbert said, we have the span of the data is the whole space whenever n is greater than the dimension plus 1. But we have never. And this point has very important implication. Implication with respect to invariance. We cannot impose invariance. Why? If X is Gaussian, with mean mu covariance operator C, and H is a bounded linear operator, then we have that Ax is also Gaussian with this mean and this covariance operator. But because of the strict inclusion, we cannot impose this assumption, because this is the span and we test for the data, we can get this other span that has nothing to do with the other. So we cannot impose invariance. And the lack of invariance has important consequences. What are the main consequences? The main consequences is that the null hypothesis will depend on the true value of mu and the covariance operator, which also implies that the null distribution we have to approximate some way. For example, bootstrap. Second limitation. Recall that the VHP compares the empirical characteristic function of the residuals to the standard normal distribution. But in L2, we don't have a standard normal distribution. Doesn't exist. Oh my God. Don't worry, this is not a big problem, because it can be seen that the VHP can be rewritten this way, where here phi n is the empirical characteristic function of the original data. This is the estimator. Phi t mu sigma is the characteristic function of a normal law with mean mu covariance sigma, and this is a distribution function. Forget, depending on beta. So we can imitate this second expression, and we propose this statistic, where here phi n is the empirical characteristic function. Here, this is our function in the sample. This is an estimator under the null, and Q is a measure on H. What measure? We will see later. Okay. Well, a first point is the following. This statistic is in some sense similar to that proposed in this paper. And this author argued that Q must be chosen so that the resulting statistic should be tractable from a computational point of view. Keep the idea by the moment. Another version of the VHP is the following. We have the following characterization, which is similar to the characterization that we saw to propose as a conversion of the VHP. Based on projection. An element is normal distributed if and only if all projections are univariate normal. So we could consider all projections, calculate the univariate VHP, and integrate. And then we can consider this test statistic. Here, this is inside is the VHP calculated for the projected data. And Q is, as before, a measure on H. Okay, practical calculation. Because we have a test, but we need to apply the test. To apply the test, the first thing we must do is calculate the test. Can we calculate? No. Exactly, no. But we can approximate by Monte Carlo integration. If Q can be easily sampled, we can sample a high number of functions and then approximate as usual. This is no problem. Second, consistency. Of course, forget about invariance, forget about what is the limit? The limit for the first test statistic is that. This is the limit under easy conditions. Here, the integram, TDF, has this expression, which is a continuous, as a function of f, is continuous. And the null is false if and only if there is one function so that TDF is greater than 0. So, to get consistency, it's enough to take a measure giving positive probability to all balls. This is easy also. This is for the first test statistic. For the second, we have the limit has this expression. Here the integram is that, has this expression, and the same reasoning apply. Well, I forgot to say that both the statistics, the limit under the null is rather complicated. In fact, it's really ugly. It's a linear combination of chi-square random variables where where the coefficients in this linear combination are the eigenvalues of set really ugly operator. So I skip. 5 minutes, yes. Just to finish, I'm going to show you some results. I want to say that the work is still in progress, and we only have a few numerical results. Under the null, we consider a standard Wiener process, and to study the power, we consider the 11 first element of the Fourier basis, and take a coefficient, the following. For the alternative 1, all the coefficients are half normal. For the alternative 2, these are half normal, and the other are standard normal. And in the alternative 3, these 3 coefficients are half normal, and the other are standard normal. And these are the results for n equal to 50. This is the direct approach, and this is the projection approach. We see that the level is kept. Of course, yes, to get the p-values, we apply a bootstrap, because as I said before, we don't have invariance. This is okay. This is a bit liberal. Here we took beta equal to 1, but maybe if we take another beta, we get better results. But quite reasonable. We see, and we move farther apart from the null, which is alternative one, the power increase. Observe that the approaches are quite different, but the power are close. It seems that it is a bit more powerful, but he's a bit liberal. So, taking into account that, the power are quite close. We should include it in our simulation. The only competitor that we can include is the projection, the random projection by Cuesta Alberto and others. But it is working. This is the end.
Wait. You need to.
The measure, yes. I forgot the measure.
Oh, okay.
I have taken the measure also the standard Wiener, because the standard Wiener is really easy to
All I was asking is, how does one pick the measure? Just to repeat.
Sorry?
Sorry. Yeah, go ahead.
Yes, the standard measure, the Q.
Yes.
Yes. I took also the standard Wiener. The standard Wiener.
Okay.
Why? Because it's very easy to generate samples, to sample, yes. That's the only reason. There are other reasons, but this is the main reason. Because we need some technicals, we need this technical condition, which is satisfied by this process. But we could. In general, all technical reasons we need are satisfied by any Gaussian method. But the easiest to generate is that, sure.
I have a lot of questions. I like this a lot. And since she's my friend, I will ask her a lot of questions during next month. No, but I like that a lot. And I have a question on data. No matter data are functions, you don't see them continuously, you have a grid, so you observe them on a grid. Okay. If the process is Gaussian, then having the estimation of the covariance operator and the mean function, everything goes smoothly, and no matter how you interpolate, you'll get a Gaussian thing. What happens if the data are not Gaussian? I mean, what happens under alternatives with this? Because now you interpolate, and who guarantees that the covariance operator, somewhere where you have not seen the data, but you have the interpolation because you have your functional data?
What happens when we have sparse data?
You have sparse data. No matter how close they are, there are holes.
I know what you mean. I don't know. Yes, because here I don't have a real data example. So here we are assuming that we have observed the data in a dense set of points. We have to study this case. Sure. Yes. Yes.
So we now have the coffee break. I would like just to point out you to Alberto. He's our photographer today. So he's a high school student doing his internship here, so he's a bit shy. Anyway, if you want to ask him pictures and so on, no problems. Then we will publish the best ones on the website. So thank you. Oh, hi.